Okay, so like I mentioned, we're going to do proper orthogonal decomposition today. This is a multivariate statistical method, and it's really aimed at trying to extract from the data a simplified or compact representation of that. So POD has many, many different names. One of the more common ones is the Karhunen-Love decomposition. And if you ever read a paper on POD, they tend to cite like 6 papers from the 1950s and 60s of the people who created this algorithm. And in general, it's very related to what's known as principal component analysis, which is a very popular machine learning technique. In fact, if you do POD, you get back a full representation of the data, and when you truncate that representation down to a few terms, you get what is known as a principal component analysis, or PCA. And both of these are then related to singular value decomposition, and in fact, we're going to end up using singular value decomposition to compute to apply POD, we'll say. Okay, so in general, POD is used for order reduction, and in this case, order reduction by projecting some higher dimensional data into a lower dimensional space, and then truncating that representation in that lower dimensional space, keeping only a few of the projections, and then going back into the higher dimensional domain from there. Also, things like feature extraction, where we're trying to reveal something that is relevant in the data, some kind of connection between them that is unexpected and not apparent from the raw data itself. And so we'll see a few applications in this chapter. We'll just look at some feature extraction, and then in the worksheet you're going to do both this order reduction and the feature extraction. And in chapter 10, we're going to end up applying the POD as a way to detect nonlinear resonances in response data. Okay, so the key idea of the proper orthogonal decomposition is basically to reduce a large number of interdependent variables. In this case, we're thinking of like displacement responses of a multi-degree of freedom system. They're interrelated or coupled together just through the structure itself, the physics of the structure. We want to reduce that into a much smaller number of uncorrelated variables while maintaining as much of the original variation in the data as we can. And so you'll often see POD applied to nonlinear problems ranging from areas like fluid dynamics to structural dynamics to all kinds of areas. But even though you can apply it to nonlinear systems, it only will produce the best linear approximation of the data. So you can apply it to a nonlinear system, but you're going to get back what could be called the best linear approximation. That does not mean that it's not useful, it's just going to be linear in that sense. All right, we're going to go through the mathematical formulation of it, and then we'll see how we can actually compute it as well. All right, we're going to consider just some field theta x of x and t on some domain omega. And we're going to start by separating this field into a mean and some time varying part, and then we're going to just study that time varying part. And this decomposition is simply that theta of x comma t is equal to that mean, mu of x, plus a sigma. All right, so I used phi here, but we actually want to use sigma. So in your notes, you're going to want to make a correction right there where I circled it. Because we're going to use phi as our basis function. You can see that at the bottom of the page. So that should be a sigma. Should be sigma of x comma t. So it's a spatially varying portion of this signal. And let me just correct my notes. Okay, so what we're going to do is we're going to consider discrete times, or in this case t sub k, and we're going to consider that to be a snapshot of the system. So we have some response at that time, and we can say then that sigma sub k of x is equal to sigma of x comma tk. Simple as that. And so in a sense, this is in some sense sampling, but not necessarily digitization as well. And it's only sampling in time. so far. So given this snapshot, or a set of snapshots, the POD is aimed to obtain the most characteristic structure, which in that sense is some shape function phi of x, of an ensemble of those snapshots for that field phi or sigma of x comma t. And this is just equivalent to finding the basis function phi of x that maximizes the inner product between sigma sub k and phi of x, or we can write that as an optimization problem where we want to maximize the following square bracket, a absolute value symbol, triangular bracket, and then sigma k comma phi. We're going to close the triangular bracket. That represents our inner product. Another line that represents our modulus operator, modulus squared, and then square bracket, and we're going to take an average over that. With the following constraint, that the norm of phi, norm squared, is equal to 1. So again here, the triangular brackets represents our inner product. That's what we used in chapter 8. The single vertical line pair represents the modulus. So you could apply this to complex signals if you wanted to. We'll only do real signals, real valued signals, but you could do it to complex signals. And then the pair of double vertical lines denotes the norm, and then the square brackets with the subscript AVG, that's our averaging. It's an ensemble averaging in this sense. Okay. So equation 6 simply means that if the field sigma is projected along phi of x, then the average energy content is greater than if that field is going to be projected across any other basis function. From here, what we're going to do is take that constraint, add it into the equation above, that maximization, using a Lagrange multiplier, which we can then write this as J, which is a functional acting on our basis function phi, is equal to that ensemble average of the modulus of the inner product of sigma k phi, that's the modulus squared, and then ensemble averaging, minus some lambda value times the quantity, the norm of phi squared, minus 1. So we've built in this constraint into the functional using a Lagrange multiplier. Okay, so when you have a functional and we're trying to maximize it, the maximal value will be found when you take the derivative of that functional and you set that equal to 0. Or the extremum of that of equation 7 is just reached when we have its derivative equal to 0. And we're going to skip a bunch of steps here, but you can show that this is equivalent to that the integral over the domain omega applied to the quantity sigma k of x times sigma k of x prime, and this is an ensemble average multiplied by phi of x prime dx prime. This is equal to lambda times phi of x, and this integral, sorry, not the integral, this ensemble average term, this is known as the average, or it's equivalent to the average autocorrelation function. Which is something that you can look up relatively easily. Sorry, what?
Equation 7, what is J?
J is just the functional. That's all. So J is the representation of this optimization problem that we had up here with that constraint built into it. So it's just expressing the same thing, but now adding in that constraint. That's all.
And does that make the parameter is lambda 0 or not? Because after we said the modulus is 1. So the lambda portion of the equation is relevant.
So, all right, so if you were to find a perfect basis that captured that, then sure. Well, you won't, though, is the thing. Because it's not going to be a perfect projection. And we'll see some numerical examples where we can show that these basis functions, actually, let me come back to that point in a moment, because we're about to introduce terminology that's relevant here. Okay, so the solution to equation 6 is given by a set of orthogonal eigenfunctions, which we'll call phi sub I of x, which are also satisfy this integral 8. You can kind of see how it's comparable to like an eigenvalue problem in general, in the sense that lambda is now your eigenvalues for this integral operator. In that sense, once you find these phi sub i's, we call those the proper orthogonal modes. That's just the name of them. Okay, so to go back to the question here, these lambdas will most likely not be equal to 0 in this case, just given the way that this is set up. However, if you have linear data and certain conditions apply, you'll find that the proper orthogonal modes are equivalent to the linear normal modes of the structure. And we're going to see an example where that's true. And in those cases, you'll find that, well, the palms capture that data perfectly and decompose it perfectly. Those particular conditions we will see are not often met, are very rarely met in general. Okay, so in terms of what you guys will actually be doing, you won't really be solving this ever. We're going to use numerical techniques to do this. But at least you'll have kind of the background of what we're doing, what we're talking about. Okay, so for each phi sub I of x, we will also have a lambda sub I, which is our eigenvalue, and we call these the proper orthogonal values, or the POVs. Okay, so these palms, which are similar to mode shapes in a sense, they capture kind of this, if we're thinking about displacement data across a structure, they'll capture the spatial variation in that sense, in the same way as a mode shape captures spatial variations. In that sense, we can actually use the palms as a basis for the decomposition of our original time-varying field that we were interested in, the sigma x of t. We can write here that sigma, let me switch colors, sigma, function of x and t. We can write this as being equal to, for a continuous system, we're going to have I equals 1 all the way up to infinity. If we have a discrete system or a discrete data set, then it will go up to the number of degrees of freedom that you have in the data. This is some infinite sum of some ai of t times phi I of x. Very much like you would see when you solve like a partial differential equation or a modal expansion as well in those cases, except in this case, instead of using some type of mode shape that's derived from the underlying equations, we're using these proper orthogonal modes. Okay, so these coefficients ai of t are going to be uncorrelated, and what that means is that if we compute the ensemble average, ai of t times aj of t, this will be equal to delta ij times lambda I, where this delta ij is the Kronecker delta, which is equal to 1 if I is equal to j, and then 0 if I is not equal to j. And they are determined via the inner product between sigma x comma t and vi of x. In the same way you would do like a Fourier projection. In that case, your basis functions are sines and cosines. Or you might do a modal projection. All right, so the POM associated with the greatest POV, or the POV that has the highest value, that POM is going to be the optimal vector to characterize the ensemble of snapshots. So it captures the greatest representation of what is going on in that data set. So then the second POM, the one that is associated with the POV that has the second highest energy, is then going to be optimal to characterize the ensemble of snapshots when that is restricted to some space that's orthogonal to the first POM, and so on, to the third and fourth, and so on. All right, so again, these modes are all orthogonal. They may represent real physical mode shapes, but most likely they're not going to represent that. We'll see in a little bit what the conditions are. Okay, so another thing you can characterize is the energy that's contained in the data, and it is defined to be the sum of all of the proper orthogonal values. So we'll just say that E here is equal to lambda I divided by, I'm one step ahead, we're going to sum here from j equals 1 to infinity of lambda j, and we're going to write that in shorthand notation where we just say sigma j lambda j. So simply just summing up all of the proper orthogonal values gives you the total energy contained in that data set. And you can then use this to define the percent energy captured by each POM. And then in the case of the ith POM, we'll have EI is equal to lambda I divided by the total energy, or the summation over j of lambda j. Okay, so while you can apply the POD method to continuous data, you're typically going to apply it to discrete data. When applying it to continuous data, it is very cumbersome computationally, and we're not going to really go into discussion of how you do that. Instead, we're going to focus on applying this to data, since this is a data-driven course. Okay, when it comes to applying this technique to discrete data, there are many, many different options, and we're just going to write down 4 different examples, and then we're only going to look at singular value decomposition. So the first is you can compute what are known as the eigen solutions, meaning the eigenvalues and eigenvectors of the covariance matrix. Second is to use the singular value decomposition, or SVD. Third is that you can use what are known as simple learning rules. And the fourth technique that I'll mention, and this is not an exhaustive list, there are certainly other techniques as well, is that the fourth that I'll mention is that you can use auto-associative neural networks. You could probably expand that to like an autoencoder as well. So in our case, we're just going to use singular value decomposition, just because it is easy, and these days computers are power enough to handle most experimental data sets when it comes to this. Though there are times where you might run into like memory issues. For example, I tried to compute one this morning, and it required like 132 gigabytes of RAM of memory to compute this matrix. And when that happens, you add in MATLAB, you add a condition called econ, and it does it in a different way that uses less memory. I don't know. My point is that in general, SVD is easy, and modern computers can handle it. And when you can't, there are alternative algorithms already implemented into the SVD code for you to use. Okay, so we're going to consider a real valued n by m matrix, which we'll call big X. And for any real n by n matrix, there exists some factorization called the singular value decomposition, or the SVD. And this allows us to write big X as being equal to U times big S times big V. And that V is then transposed. And in this case, this U here, will represent the temporal variation. The V's here represent some spatial variation. But generally, we're going to end up doing a multiplication of U and S to find the temporal variation of each palm. Okay, so here U is an n by n matrix. So if you recall, big N, it will be the number of points in time, that is the number of sampling points. Big M is the number of degrees of freedom, or the number of sensors that you have in your data set. So big U is an n by n orthonormal matrix, and it contains what are known as the left singular vectors. Big S is an n by m, which is a pseudo-diagonal matrix. That means that all non-zero entries follow a diagonal, but it's not a square matrix. So meaning once you hit the far end of the matrix in terms of diagonal, everything below that will be zeros. And also it's semi-positive definite, and it contains the singular values S sub I, and then big V is an m by m orthonormal matrix, and it contains the right singular vectors. So in general, the palms are equivalent to the right singular vectors, big V. So by computing the SVD, we immediately get the palms right away. The POVs are related to the singular values through the following. We'll have that lambda I is equal to SI squared divided by n, and again, big N here is the number of samples. And then, like I said, the left singular vectors represent the temporal evolution or temporal variation. Let's actually correct this. All right, so I've just crossed out evolution of the palms, and it's more of a temporal variation because we'll end up doing the multiplication of US to find the temporal variation of the palms themselves. Okay, so I'm going to briefly scroll up to equation 9 here. So previously we created this decomposition where we had some time varying component AI of t. we're going to build a similar decomposition using the singular value decomposition. Scroll a little bit too far. So by doing that, what we can say here is that big A of t is equal to u times s, which will then give us an n by m matrix containing the time or temporal variation of each of the palms, and then we'll find that big X is equal to A of t times V, or that the mth degree of freedom is equal to the summation from j equals 1 to big M of A j of t times V jm, where VJM, that subscript JM, means the jth palm at the mth coordinate or degree of freedom. Okay, so if you want to compute the palms without using like the SVD algorithm in MATLAB, what you can do is you can say that you can let big R equal to X times X transpose, and we'll let big P be equal to X transpose times X. You can find U and S by computing the eigenvectors and the roots of the eigenvalues of R respectively. So that gives you the temporal variation and the singular values. And then if you want to find V, what you do is you compute the eigenvectors of P, and this is by the simplest approach you can implement in terms of computing these. When you do this in the worksheets and in future homeworks, you can just use the SVD algorithm that's built into MATLAB. Okay, and then one more thing before we talk about physical interpretation is that you can only apply the POD to data sets that are all of the same type. And that means that all of the data set, all of the signals have to be displacements, or all of them have to be velocities or strains. They cannot be displacements and velocities. It will not work on data sets like that. And if you're interested as to why, I can share a paper that goes through this and explains that. But we're going to skip that. In this class, you'll just apply it mostly to displacement responses, so you won't run into that issue. All right. Let's talk about the physical interpretation of POD, and then we'll take a look at some examples where it's applied to some 2-degree freedom systems. All right, so first, given that the POD is computed using response data, the outcome is going to be signal dependent, and this can be a good thing, and it can also be a bad thing. But in general, this is the biggest weakness of the method, and this is what prevents us from giving some general physical interpretation of what the palms are or their temporal evolution overall. But it's also a benefit to us because when, for example, in a nonlinear transient response where the actual nonlinear mode shapes are changing over time, we can use the palms as a way to track that kind of behavior. So it is a benefit in some way, but in terms of trying to understand exactly what palms are physically, it prevents that. All right, so the palms can bear some resemblance to physical mode shapes, or in particular cases that we'll see, they can be exactly the same under special conditions. And the key thing that we need to realize is that the proper orthogonal modes are going to be orthogonal to each other, whereas if we think about linear normal mode shapes, those are orthogonal to the mass matrix. And then specifically, the palms satisfy the following condition: phi transpose, and these are now vectors in this case, times phi j. This is going to be equal to delta ij, or again, that's still this Kronecker delta. So they satisfy that condition, whereas if we consider mode shapes ci and cj, the condition is that ci transpose times the mass matrix M times Cj, this is equal to delta Ij, and Ci transpose times Cj is not necessarily equal to delta ij in general. And as soon as we're using something like a finite element model, then it's automatically not going to be true. Okay, so given these orthogonality conditions, the one in 16 and the one on the left of equation 17, I should also mention here that the Ci and Cj are what are known as mass orthonormalized, meaning that this product in equation 17 results in either a 1 or a 0. If they're not mass orthonormalized, then you'll either get a 0 or some non-unity value representing the modal mass. So the key thing here is that the palms are only going to be identical to linear mode shapes when the mass matrix is proportional to an identity matrix, which is generally true in a lot of like simple academic examples, but is never true in real life, where you have continuous structures. So we're going to take a look at an example here, which is just a 2-degree freedom system without any damping in it. I'm going to write down the equations of motion, and then we're going to look at some simulations and look at the palms based on those simulations. So the first equation of motion is just going to be m1 x1 double dot plus k1 x1 plus k2 times x1 minus x2. That's equal to 0. Second equation of motion is going to be equal to m2 x2 double dot plus just k2 times x2 minus x1. This is then equal to 0. We're going to set everything equal to 1 in the first case, and then we're going to do part A and part B. Then we're going to repeat it for when m2 is equal to 2 instead of 1. So in the first case, we'll look at these. The mass matrix will actually be the identity matrix, and in the second case, it will not be an identity matrix, and it will not be proportional to an identity matrix. Okay, so I just chose to simulate up to a time of 1,000 in this. You could get away with doing up to a time of 100 or something smaller as well. Given that there's no damping, you can do that. I just chose 1,000 because whatever. And also I'm going to simulate for 0 initial conditions except for x2 dot is equal to 1. You can change the initial conditions. This stuff still will work and hold just fine. This is just what I've chosen. After we simulate it, we're going to apply the SVD to the two displacements. We're going to compute the resulting palms, and we'll compare those with the mass orthonormalized mode shapes. Let's see. Okay. All right, so here's a response where both masses are equal. There's not really a lot to say about the response. You can see the displacement, you can see the wavelet transforms, and then you can see the Fourier transform beneath that. There's just two linear natural frequencies, nothing too interesting. If we go over and we take a look at the mode shapes and the palms, it's kind of hard to display mode shapes in this kind of configuration where something like a beam or a wing, it might be much easier to visualize what it looks like. In this case, what we can see in the first plot to the top right, you just see that both masses have a positive amplitude, and in this case, the second one has a second degree of freedom has a higher mass, a higher amplitude. And you can see that the palm lies right on top of that mode shape. The mode shape is in black with a circle, and the palm is in dashed red with just a little X. Same with the second palm and the second mode shape, they lie right on top of each other. So in this kind of case, you can see that the palms and the mode shapes are exactly the same. What the heck? All right, just take a look at a case where M2 is equal to 2 now. And you can see that, I'm just going to focus on the palms here on the right. You can see that the palms are similar to the mode shapes in terms of signs and somewhat overall amplitudes. And even if we think about that slope between the 2 points, they're similar, but they're not exactly the mode shapes as well. And that's because the mass matrix is no longer equivalent to an identity matrix. And so what will end up happening, and you'll see this in the worksheet, is that when we do the projection onto the palms and try to compute their temporal evolution, we won't get a perfect decomposition of the frequency content. So what I mean by that is that if you were to do a decomposition of these signals using the mode shapes, you would end up getting one time series that has this frequency in it, and then another time series that has that frequency in it. When you do it with the palms, if you do it with the palms in the first case, you'll still split them up and get a nice segregation of the two terms. But in this case, what you'll find is that the temporal evolution of those two palms will actually have some contamination of both modes, of both natural frequencies. And if there's many frequencies, like what you'll see in the worksheet, you'll see that the temporal evolution will have multiple components, and it's not a pure decomposition. Okay, any questions?
Could you say that again, the second part that you're saying that it is not proportional to identity matrix, this mask. So what happens? I don't see the other component in the X2, right? There's no other frequency there.
It's there.
It's there.
Okay, you look at the Fourier transform. In sine, you can see that there's a clear peak there. So it's there, but it's not strong. It's not as strong as the first term, but it's still there. And in the wave of the transform, it's hard to see on the print. I can barely see it on the iPad here, but it is there, and you can see it in the Fourier transform.
Yeah, in
But-
the Fourier it's okay, but I mean in the regular transform it was not clear.
Okay, it's there. That's what I can tell you. Would you say that it's very strong or dominant in that signal? No, but it's still there, is what I would tell you.
What does that mean physically?
It means that the amplitude of that particular mode at that degree of freedom is small
Right.
compared to the first mode at that degree of freedom. If we come up here, you can see the two components. So by increasing that mass, we have actually lowered the amplitude of it in that component. Okay.
But what does that have to do with contamination? Like, what did you mean by contamination?
You'll see it in the worksheet. But basically, we're trying to, if the palms are perfect mode shapes, then we can go back and do this decomposition shown by equation 16 here. That will give us a temporal evolution, 16 and 17. And that A of t for a particular palm will only have a single frequency in it if the palms are equivalent or exactly the mode shapes, which is only true when the mass matrix is equivalent to an identity matrix, and which means that likely that's never going to be true for any kind of application of this, other than some simple academic system where you get to choose the mass matrix, or someone gives you a mass matrix that is already proportional to an identity. So my point is that the palms are not the mode shapes, but they're similar. And we can end up using that to our advantage. And when you do the worksheet, you'll see what I mean about this contamination. For example, in the worksheet, you'll find that the temporal variation of the first palm is very strong in the first mode, but has weak responses in the other modes. Where if it was a perfect decomposition, it would not have any response in other modes. It would only have it in one mode. And you'll see that in the worksheet. Okay, so MATLAB code is included here. The SVD computation is simply done here. It's just using SVD. And for this particular data set, we didn't need to use the econ flag. Okay, so the nice thing about POD is since it's signal dependent, it can be used to capture energy dependence of nonlinear systems, and we're going to see this in this next example. So we're going to take that same system, except now we're going to add a nonlinear spring to the one end, and I'm just going to rewrite the equations of motion just to remind you, or rewrite the new equations of motion. In this case, we're still going to have m1 x1 double dot plus k1 x1 plus k2 x1 minus x2, that's equal to 0. And the second one we'll have m2 x2 double dot plus k2 times x2 minus x1 plus, in this case, we'll have alpha times x2 cubed equal to 0. So I'm just going to set all the parameters equal to 1, but you should feel free to go and take this code and change the parameters and see how the palms change with different parameters. We're going to set them equal to 1 for simplicity here. Then I've also computed the nonlinear normal modes for this using the method known as NNM cont, which we discussed previously. I think it was in chapter 5. We're not going to look at the frequency energy plot here. I'm just going to take the periodic solutions, or you might call them nonlinear mode shapes if you felt like it. I'm going to use those and compare the NNMs, or the periodic solutions of the NNMs, to the palms, as well as the underlying linear mode shapes. And we're going to do this for varying initial velocity applied to that second mass. Okay. So again, I've included the displacement response, the wavelet transforms, and the Fourier transforms. We're not going to spend too much time talking about them, except that in this case, our mass matrix is an identity matrix, so we should find in a linear regime of motion that the palms should be equivalent to the underlying linear normal modes, and in this very low velocities, so are the periodic solutions of the nonlinear normal modes. And you can just see that they all line up on top of each other. If we go up a little bit in velocity, we'll start to see a small deviation in the palms and the periodic solutions compared to the mode shapes, at least in that first one. We're not going to really look at this one too much. Here you'll see that as we go up again in energy, here the periodic solution of the first NNM starts to break away from the underlying linear normal mode, and the palm tracks that as well. In the first, at least in the first mode, palm, etc. In the second one, the palm is actually a little bit off from the others. We're going to go higher in energy, and here's a case where our palm will no longer start to match the periodic solution of the nonlinear normal mode or the underlying linear normal mode, but still has the same kind of shape in general. Going up again, higher in energy, you can see here that now the amplitudes have actually reversed in that first mode in terms of which degree freedom had a higher amplitude. And the periodic solution shows this, and the palms also track that, which is not represented by that linear normal mode shape. As we go up, we'll start to see the palms will vary and be a little bit different than the NNMs, but still kind of capture that overall behavior. If we go up to even higher energy, we end up getting in a sense, a mode conversion, in which we'll skip the word in mode conversion, and I'll just simply say here, at this energy level, the palm with the highest energy, which is our first palm, is actually more representative of the second mode rather than the first mode. So the palms are organized by the amount of energy that they capture or represent, with the one with the highest energy, regardless of what mode shape its similar is, that is the first one. Whereas, of course, nonlinear normal modes or linear normal mode shapes are organized based on frequencies. Okay, so in this case, the first palm is more representative of the second mode, and the second palm is more representative of the first mode. And this has to do with some type of mode switching that occurs in the NNMs, which we won't go into. Same thing at higher energy. Eventually, this actually becomes a linear response in some sense, and the palms will start to match and line up with the actual periodic solutions of the NNMs, although in this case you can see that they've also switched in terms of amplitudes, and the second palm is now more representative of the first mode, and the first palm is representative of the second mode. Okay, so one more thing, you can see the code there that I'll say before we do the worksheet, is that if you're looking at transient response data, you have two options. You can either apply POD to the entire signal or some small portion of it, or you can do like a sliding window where you take a window and then step forward some amount, look at that window, and so forth. And if you do it with a sliding window, you can track how the palms will change over time, and we'll end up using this to look for nonlinear resonances next week.